Hello everybody, how are you? And welcome again to our chemistry session. Today inshallah we'll start a new section number 4. It will be about solubility equilibrium. So here's the main objectives of this section. Number 1, inshallah by the end of this section we'll be able to explain what is meant by solubility product constants and calculate their values. Number 2, calculate solubilities using solubility product constants and carry out calculations to predict whether precipitates will form when solutions are combined. So today inshallah we will start with the first point. We will explain the meaning of solubility product constants, and we will know inshallah how to calculate their values. So a saturated solution, we know that a solution can be categorized in terms of their concentration into dilute solution, concentrated solution, saturated solution, and supersaturated solution. So a saturated solution contains the maximum amount of solid possible at a given temperature in equilibrium with an undissolved excess of the substance. Okay, so here we have an important point. A saturated solution is not necessarily a concentrated solution. So guys, assume that we need to prepare two solutions. The first solution is made up of salt, for example NaCl, sodium chloride, or a certain amount of water, for example 250 ml of H2O, and we need to prepare another solution that is made up of another kind of solid, and here we will use, for example, another type of chloride. Let us say silver chloride. Okay, so now we will start to add for both of the solution, of course we are using the same amount of water, which is 250, and then we will start to add for example 10 grams of each of the solute or each of the salt to the two beakers that you have. So now, as we know guys, for the sodium chloride is a kind of chloride that is highly soluble, so it will start to dissociate their ions quickly and it will reach the saturation. But before it reaches the saturation, after you add a certain amount of or certain grams of this salt, probably it will become concentrated, right? So it will reach the concentrated level, and then if you add more and more of this salt, which is the sodium chloride, it will reach a saturation level at which you cannot add more salt, otherwise it will precipitate at the bottom of this beaker. Okay, so for sodium chloride, because it's highly soluble, we assume that it will reach the concentration level. It will become concentrated solution, and after that it will may become saturated. But for example, for the silver chloride actually is an exception, because most of the chloride are highly soluble. We have exceptions like sodium, for example, silver chloride and lead chloride. They have a low solubility, so that's why they may reach the saturation level, or the level of saturation, without being concentrated, because the silver chloride is not highly soluble in water. Okay, so that's why we always say that a saturated solution is not necessarily a concentrated solution. Okay, so because of that guys, we need to use a certain kind of measurement that will help us to determine which solute has a high solubility, which one has a low solubility. And this measurement will be, guys, the solubility product constant. So actually the solubility product constant is used, why? To describe how soluble a substance is. So as we said, for example, sodium chloride has a high solubility, while silver chloride, for example, has low solubility. So guys, the solubility product constant KSP of a substance is the product of the molar concentrations of its ions in a saturated solution, each raised to the power that is the coefficient of that ion in the balanced chemical equation. So before we start to calculate the solubility product constant, we need to what? We need to write the balanced chemical equation. So for example, here we have the equilibrium equation for the dissociation of silver chloride. HCl, solid salt, will dissolve and yield the silver cation and the chlorine anion. So as we can see, 1 mole of HCl yields 1 mole Ag and 1 mole chlorine. Okay, so again guys, the solubility product constant, or KSP, as we said, used to describe how soluble a substance is, and it's and KSP of a substance is what, guys? Is the product of the molar concentration of the ion that will be produced from this kind of salt in a saturated solution, each raised to what? Each raised to the power that is the coefficient, guys, of that ion in the balanced chemical equation. So guys, it's important to write the balanced chemical equation, since we are gonna include the coefficient of each of these ions in our calculation. Okay, so now the equation for the solubility equilibrium expression for the dissolution reaction of HCl, for example. How can we write the equilibrium expression or the solubility equilibrium expression for any kind of salt, guys? KSP is equal to what? Concentration of the ions, okay, raised, as we say, to the power that is equal to the coefficient of the substance. Okay, so here, as you can see here, we have 1 mole of silver, 1 mole of chlorine, so it will be raised to what? To 1. The concentration of each ion raised to the power equal to their coefficient in the balanced chemical equation. And guys, here we can see that we didn't include what? We didn't include the concentration of HCl. Why? Because usually we do not include, guys, the concentration of solids and pure liquid. Why? Because we expect that they will not undergo any change, so their concentration will stay constant, so there is no need to include their values in our expression or in our calculation. Okay, so the equilibrium expression is written without including the solid species. So let us see here another example, guys. We have calcium fluoride. Calcium fluoride. So the equilibrium equation will be as following: calcium fluoride, the salt, so the salt will dissociate into calcium and 1 mole calcium and 2 mole what? Fluoride. So here we should make sure that we have the balanced equation. Balanced equation means that we have what? The same amount of atoms for each element on the both sides. Okay, so now the expression of the solubility product, or for KSP, is equal to what? As we say, concentration of the product raised to the power that is equal to their coefficient. So here we have 1 mole of calcium, so you will raise the concentration of calcium to 1. And for fluorine, we have 2 moles of fluorine, so you will raise the concentration of fluorine to a value equal to 2. Okay, so now the solubility of calcium fluoride is 8.6 multiplied by 10 to negative 3 per 100 grams of water at 25 degrees Celsius. If we want to express it in moles per liter, we need to convert the grams into mole, and the volume of water here 100 into 1 liter, 100 grams into 1 liter. Okay, so tomorrow inshallah we will learn how to convert this value into mole per liter. But for today we need to focus on how to write the expression for the KSP and how to write a balanced chemical equation Okay, so determining KSP for reactions at chemical equilibrium, we have 3 main steps. Step number 1, write the balanced chemical equation. So remember that the soluble product is only for those salts that have low solubility, guys. Here we are measuring KSP for salts that are less soluble, that cannot be soluble. But for soluble salts such as sodium chloride, for example, ammonium nitrate, we don't need to calculate their KSP. So number 2, make sure that the reaction is at equilibrium, as we said. And then chemical equations should always be written so that the solid salt is the reactant and the ions are the product, okay, as we showed you in our example. Okay, so step number 2, write the solubility product expression. To write the expression, write the product first of the ion concentrations, then concentrations of any solid or pure liquid that take part in the reaction are left out. Why? Because they never change. They have constant value, as we say. Step number 3, complete the solubility product expression. To complete the expression, raise each concentration to a power equal to the substance's coefficient in the balanced chemical equation. So remember that KSP value is dependent on temperature, so we usually measure the KSP value for most of the salts at 25, but of course if you change the temperature, KSP value will change as well. So if we have this question, guys, and we need to find KSP, we'll do it in this way. So calcium chlorine or calcium fluoride dissociates to yield twice as many fluorine ions as calcium, as we explained this chemical equation. So for each 1 mole of calcium fluoride, we'll have 1 mole of calcium and 2 mole of what? 2 mole of fluorine. Okay, so suppose the concentration of calcium is equal to this value and the concentration of fluorine is equal to this value, and the unit is we are using here is mole per liter. Then have to find KSP. KSP basically is what? Equal to what? Equal to the concentration of each of these ions raised to their powers. So KSP is equal to, you will only plot the value of the concentration and you will raise them to the power that is equal to what? To their coefficients. We have 1 mole of calcium and we have 2 mole of fluoride, so you will raise the concentration of fluorine, to 2. Then you will do your calculation, and in this case KSP is equal to 5.3 multiplied by 10 to negative 9. Okay, now guys, here we have a table that will show us the solubility product constant at 25 degrees Celsius for different kinds of salts. Okay, for HCl we have this value 1.8 multiplied by 10 to negative 10, for example. What else do we have? Okay, calcium carbonate is 5 by 10 to negative 9, and so on. Okay, so later we will see how we can use these values or these constants. So for today, that's all, guys. See you inshallah next week.